Okay, so administrative stuff first. We have homework due Friday, right? That's homework 7. That's on the short side. There are 3 problems, none of which, in my view, should take very long. I'm happy to provide help. I can provide you help right after class if you like, or we have official office hours on Thursday. We have lab 4 due next Friday, right? No lates. For labs 4 and 5, you can type the report. In fact, please type the report. Okay, the standards, you know, are something I plan to pick a couple and have them presented, and then you vote on one, and that one we're going to post, and it's going to be part of the lab 5 assignment. So it needs to be typed ultimately, and I think it's better if we just do it as part of the initial submission. For both lab 4 and 5, you upload everything in the Blackboard site. You don't have to put anything in the Dropbox. Just upload it through Blackboard. So that's let's see, that's homework 7, lab 4. I think that's it. Any questions? People started lab 4? Yeah? No? Okay. I recommend at least starting it, get a feel for it, try to send, just send like a training OFDM symbol through, or send 2 OFDM training symbols back to back, and train from the first one, and then see if the second one ends up giving you about the same frequency response. It should, right? So just try some basic experiments like that. Okay, so we're talking about coding right now. And we have a little bit more to say about coding for the binary erasure channel. And then we can start talking about how to code for more general channels like the ComCloud channel. Okay, so let me recap where we were. So we're starting our coding unit by talking about a very particular channel called the binary erasure channel, which is different from the ComCloud channel. Most of the channels we talk about in this class, in that although time is discrete, amplitude is also discrete. So you send in a discrete bit, not a continuous amplitude each time, and you get a discrete symbol out. And this very particular channel, it never flips bits. Okay, it just erases some of them and erases them independently from bit to bit. So the thought experiment we want to perform is we want to consider sending k data bits over n uses of the channel. So you get to use this channel n times. Okay, so the thought experiment is the encoder gets the string of k bits, it maps them into n bits. That n-length bit string goes through this channel. The channel randomly erases some of the bits. The decoder gets an n-length string that's not quite binary. It's ternary, so it's 0, 1, and E, and then tries to recover the data bits from it. Okay, that's the thought experiment. You can debate how realistic this is. In reality, you might just kind of keep sending until the bits get through, or you have some feedback to signal whether the bits got through or not. You can argue it's a bit artificial to just at time n just cut this off and force the decoder to guess as best it can at that point, but this is kind of like a simple model where it's easy to see the phenomenon that we're interested in, namely how to mix bits. Okay, so or why mixing bits is a useful thing to do, I guess is the way to think about it. Okay, so we talked about how to code for this channel with feedback, and then we talked about when you don't have the feedback link, one method that's particularly effective is to do what we call random linear coding. Okay, so you set up this big matrix, it's n by k. And the entries are just I, d, Bernoulli half. Okay, this matrix you hard code in both the encoder and the decoder. When the encoder gets its k bits to the k data bits, okay, you just multiply the data bits by this matrix using the binary field. Okay, so everything's mod 2, or equivalently, multiplication is and addition is XOR. Okay, so just perform this operation. You get an n-length vector. You send that. Okay, decoding is a lot harder. So for the decoder, you look at the non-erased bits. Suppose there are L of them. Okay, you let these L0 through L1 be the indices of the non-erased bits. Okay, and you just delete the corresponding rows of G corresponding to the erase symbols, and you end up with a linear system like this. Okay, so the decoder knows the Y's, it gets those through the channel, knows the G's, that's hard-coded, doesn't know what the data bits are, obviously. Okay, and so its problem is to solve for these variables given this system. Okay. So if you have enough equations and they're linearly independent, then you can do this. If the channel erases too many bits and this matrix collapses way down to something really thin, or really fat, excuse me, then you're not going to have enough equations and it won't work. Okay. So what we showed though is that in the large n, large k limit, okay, so if these both scale up and they scale up proportionally, with the proportionality constant being r, the rate, which is less than 1 minus epsilon, okay, then this overall experiment will work with high probability. The error probability will go to 0. Okay, so the experiment is you generate the k bits, you generate the G matrix randomly, you encode, you erase the bits randomly according to the channel distribution. You perform Gaussian elimination here to recover the bits. Okay, the probability that this fails will tend to 0, so long as the rate you're shooting for is below 1 minus epsilon. Okay. 1 minus epsilon we call it the capacity of the channel. That's not a term that we define in this class, that we'll use in this class, but every channel, it turns out, has this kind of sharp rate threshold below which you can make the error probability very small, like this, arbitrarily small, above which the error probability tends to be close to 1. So most channels have kind of a phase transition around a certain rate. This is not a phenomenon we talk about in this class at all, but just as an aside, I'll mention that for the BEC, this is the capacity here. So this is sort of the, the beginnings of a phase transition. When the rate's bigger than 1 minus epsilon, then the error probably behaves very differently. Okay, so this is all fine. It's a bit computationally expensive, though. When n and k are big, just multiplying by g here is going to be kind of expensive. That's like n squared complexity. Moreover, Gaussian elimination here is going to have complexity on the order of n cubed. Okay, all that's too much. So we'd really like to come up with alternate algorithms that give you the same rate performance, allow you to achieve the same rates, but have lower complexity at the encoder and the decoder. So that's what the peeling algorithm is about. So we start out by just attacking the decoders. So think of the encoder as fixed, and we're just going to replace Gaussian elimination with something more efficient, okay? Because we have higher complexity at the decoder than the encoder right now, right? N cubed here, n squared at the encoder, right? So I'll start by attacking the decoding, although we'll see ultimately this will influence both of them. Okay, so the way Gaussian elimination works, if you let G prime be this reduced matrix with the rows corresponding to the erasures deleted. So Gaussian elimination means you do like row operations to get this thing to be row echelon form, like essentially like an upper triangular form or a lower triangular form. And then you back substitute. Okay, so you find an equation with just one in the reduced form, with just one variable appearing. You read off that variable. You eliminate that variable in all the other equations, and then repeat. Okay, so you had one equation that had 2 variables in it. You eliminated one. Now you have an equation with 1 variable in it. Pick that off, eliminate it from all the others, and keep going. Okay, so back substitution. Okay, so the peeling algorithm, okay, which turns out to be a special case of something, a much broader class of algorithms called belief propagation. Peeling essentially amounts to just ignoring the first step. So don't try to do row reductions to get it in a row echelon form. Just hunt around for a row that has a single 1 in it, which corresponds to an equation with just one, where 1 variable is appearing. Right? If these are all zeros except for this one, the equation reads that this variable equals that, right? So just hunt around for a row that has a single 1 in it, pick off that variable, read out that variable, eliminate that variable from all the others, all the other equations. Now try to find another row with a single 1 in it and just keep repeating this, okay? And hope for the best, okay? Yeah?
The peeling algorithm,
yeah.
like the row that you happen to find has a erasure at the output, what do you do?
Okay, so in both Gaussian elimination and peeling, you start by just deleting all the outputs that have erasures, because those convey no information to you. Right. So delete them from Y and delete the corresponding rows from G. Okay, and just consider like the reduced dimensional problem where only the non-erased bits were transmitted to begin with, and the channel did not erase them. And then now there's no erasures to speak of anymore. So both Gaussian elimination and peeling have that first step in common, which I guess I didn't write explicitly here. It's kind of implicit in writing this system here. Okay. After that's where the difference is. So Gaussian elimination does the row operations to get you in row echelon form first, whereas peeling skips this. I should write that here. So peeling skips this. So that's one way of thinking about peeling in like a matrix form. You're just solving a linear system in a particular way. There's another way of writing it down in terms of graphs that I think is useful to be exposed to because you'll see it done this way. And also this graph way of thinking kind of generalizes better to other channels. Okay, so this like linear algebra, like Gaussian elimination thing is very particular to the binary erasure channel, whereas the graph thing I'm going to show you kind of generalizes a little bit easier. So so here's the way it works. So you create what they call a bipartite graph with like squares and circles. People know what I mean when I say bipartite graph? Yeah? No? Okay, so I'll draw an example. A bipartite graph is where you can put all the nodes into two groups, and the edges only go from one group to another. Okay, you don't have edges within one group. Okay, it's like I don't know. You have like ECE majors and you have CS majors, and like ECE majors are only friends with CS majors and vice versa. The ECE majors are not friends with each other, and the CS majors are not friends with each other. Okay, that's a bipartite. That's the first bipartite graph that popped in my head. I know that's weird. Yeah, because these things would maybe not, like in a social network, this would not be a naturally occurring thing, right? If you have a group, usually there's more edges within the group than without. I guess it depends what an edge means. So if an edge means friendship, then it's unlikely. If an edge means like animosity or something, then then it's very natural. So anyway, so the circles will represent the data bits, and the squares will represent the transmitted bits or the received symbols. Okay, so let me just draw a quick example up here so you have a picture to look at. So suppose n is 4 and k is 3. So you're sending 3 data bits over 4 uses of the channel. Okay, so we have 4 CS majors. We have 3 ECE majors. So the enrollment in CS and ECE are similar, right? And I actually had a particular pattern in mind here for these edges. So let me draw this out so my later examples are all consistent. Like that. Okay. So the point is every edge connects a square and a circle. You don't connect circles and you don't connect squares with each other. Okay, it's just squares connect to circles. Okay. So I guess if you want to connect this to the linear algebraic form of it, you have an edge from circle I to square j if g, let me get this straight here, ji, I guess, I kind of did it backwards, is 1. Okay, so just think of these as representing the rows, and these as representing the columns. Okay, and then the 1, it's a binary matrix, right? It's 1, 0. So the 1, 0 just dictate the edges here. So you put a 1, or you put an edge if there's a 1 on that row, column, pair, all the way through. Okay. So encoding, fill in the circles with the data bits. And then compute the exclusive or equivalently the mod 2 sum of all the neighbors for each square. Neighbors meaning all the circles that it's connected to. And then that's your transmitted string. Okay, so if you're, the data bits are 1, 0, 1. Okay, so in here you just take the XOR of everything it's connected to. So XOR 1, 0 is 1. This is only connected to a 0. This one's connected to a 0 and a 1, so its XOR is 1. This one's connected to all 3, so its XOR is going to be 0. Right, so 1, 0, 1, 0 is what you'd send. Okay. is basically just doing the matrix multiplication that we were doing before, just writing it in a graph form, graph theoretic form. Okay. And the graph is, you assume, is hard-coded in both the encoder and the decoder. Just like the way G was hard-coded in both the encoder and the decoder. Okay, so what about decoding? So decoding is usually harder than encoding. Okay, so first step is to populate the squares with the symbols from y. So place the symbols, I just say place the y symbols in the squares. Some of them will be erased, right? So I might end up with an E somewhere. Okay, those, just like in the G case, in the linear algebra case, we just pretend they didn't exist. So delete those squares and their edges. Containing E's and their edges. Okay, and no row echelon form here. You just look for an equation with one variable in it. Okay, and then eliminate that from the other ones, and then keep going. Okay, so in that, if that's my goal, how do I express that in graph theoretic terms? What do I look for? I want one equation that has a single. I want to find an equation with a single variable in it. So in graph theoretic terms, what does that mean? Square with one edge, right? Find a square with one edge. If none, just like terminate with an error. Say I can't solve this. Go ask Gaussian elimination. Maybe it can do it, but Peeling algorithm will not. Okay, you have a square with one edge. Let's call the square S. Maybe let's give it a name. Suppose S is connected to the circle C. Okay, we know the value of S. I mean, if you look at the way the encoding works, right? I mean, each transmitted bit here is the XOR of all the data bits it's connected to. So here, you know, if we have, once you have a transmitted bit with just a single edge, then you know what that bit, you know what the data bit had to be, right? So you got to flip things around, right? So the encoder, when you do encoding, like you know the data bits, you're trying to figure out what to put here. So you just take XOR of all the neighbors, right? For the decoder, it's the other way around. You know these, okay? You're trying to figure out what to put here, right? If you didn't know that one, if you have a square with a single edge, okay, you know this was the XOR of everything it's connected to, and it's only connected to one thing. So whatever's here had to be there, right? So just copy. So copy bit from C to S. Okay, at that point you don't need that that square anymore. So delete S and its edges. Okay, now I want to eliminate this variable from all the other equations. Okay, so that means replace all squares connected to C with XOR of the bit in C and the bit that was already there. Okay, that's the back substitution step. At that point, you can delete all the edges from C. You've already accounted for its effect on all the other equations. So just delete all its edges. And then if you're not done, just repeat. Go back to 3. So I'll say if some circles are still open, oops, sorry. Go to step 3. Yeah. From S to C, yeah. Yeah, so the decoder knows the bits in S, is trying to figure out the bits in C. Okay? So I'll do a quick example right here. Just run through this. Okay, so suppose we get 1, 0, E, 0. Okay. All right, so we want to figure out what the data bits were. So first thing to do is just populate the squares with the receive symbols. This was erased, so we're going to pretend like it didn't happen. So I'm just going to delete this square and all of its edges. Right? Effectively, just pretend it was never even transmitted. Okay, where are we? 3. So find a square with a single edge. There's 1. We now know this data bit, right? Because we know this was an XOR of everything it's connected to. And it's only connected to this. And the XOR is 0, so this had to be 0. Okay, at that point, I don't need this square anymore. I've gotten all the information out of it that I can possibly get. So my system looks like this. Okay, now this one is the XOR of these two. And I know this is 0. Okay, so this is effectively just telling me this bit. If this was a 1, then I would, I'm going to erase this edge right now. Okay, because it's 0, I can just erase it, no harm. If this was a 1, I'd have to replace this. I have to flip this bit to account for the fact I had a 1 here. But since I only have a 0, I can just erase the bit. Formally, when you erase this edge, you replace this bit with the XOR of this one and this one. But since it's 0, it doesn't matter. Okay, we're now at step, 8, right? Oh, no, sorry, I need to do this edge. Same thing here, do this edge too. Again, we don't flip the bit because that was a 0. Okay, we're not done yet. We still have unaccounted for data bits, so go back to 3, find a square with 1 edge. Here's 1. Okay, this now has to be, this is going to be the XOR of everything it's connected to. It's only connected to that, so that must be a 1. Now we don't need this anymore. This is the XOR of these two. I can write it as the XOR of that one alone if I account for the effect of that 1 there. Okay, now I'm in step 8 again. Still have data bits unaccounted for, so go back to step 3. Find the square with 1 edge. There's 1. Copy its bit down. That's it. Just the algorithm. Okay. So I'm not going to try to prove this works. I think if you kind of stare at it for a while, it's pretty clear it's what it's doing, and then it's basically doing the peeling algorithm. It's just doing the finding one row with a single 1 in it, and then eliminating from other equations and so on. The key observation to observe is that this algorithm always preserves the fact that each square is always the XOR of everything it's connected to. It preserves that property. Okay, so as such, it's never going to output the wrong bits here. It might terminate prematurely and say you can't solve this, but it'll never give you like a wrong guess for the bits. Okay, any questions about the algorithm? So this is equivalent to the, like I said, the linear algebra approach. I debate whether to even include it or not, because you can argue it's kind of redundant. We did the algorithm already. I cover it for 2 reasons. One is I found that some students are actually more comfortable with this than with the writing it in G matrix form. So there's that reason. Also, as I mentioned earlier, when you move beyond the binary erasure channel to other channels like binary symmetric channel, Gaussian channel, and so on, this kind of like peeling, Gaussian elimination, linear algebra form breaks down, because it's very dependent on the fact that the channel doesn't flip bits. whereas the graph theoretic form actually generalizes better. Okay, so you have to kind of take my word on it for that. But anyway, if you take coding theory, probably do study these kinds of graphs. Anybody taking coding theory right now? No? Okay. Never mind then. All right. So let's talk about the complexity, peeling. So we've really changed the encoding algorithm. It's essentially the same as before. It's n squared. More precisely, it's really like the number of edges in the graph, which is equivalent to the number of ones in G, which is of course no more than n squared. Okay, so there's not really much savings there. I mean, that was true even when we were just doing Gaussian elimination. We have changed the complexity of the decoder. The decoder is now about the same. It's about the number of edges. That governs the complexity. So as before, number of ones. Okay, so the way you see that, you just take this picture and kind of study the algorithm and notice like you touch each edge like once or twice. Okay, so you kind of just move through the edges and just eliminate all of them until, when you're done, there are no edges left. Okay, so you essentially just, kind of move through the edges in a particular order. And of course, the number of edges being the number of ones in G is no more than n squared. Okay, so this will go down from n cubed to n squared at the decoder. The encoder's still about the same as before. Okay, so this is interesting. There's some issues with this, though. Okay, in particular, if you're still choosing G, and trying to do the peeling, if you're still choosing G Bernoulli 1/2 all the way through, okay, then you're going to do a couple of issues. So if I choose G, the elements of G to be IED Bernoulli 1/2, in graph theoretic form, let me put this graph back up here. What did this look like? This one was alone, that one like that. I think that was the graph, right? It doesn't really matter, but okay, so if we're choosing the elements of G IED Bernoulli 1/2, it's equivalent to just selecting whether you have an edge or not between each square circle pair with probability half. Okay, so just for each possible pair here, you just flip a coin to decide whether there's an edge or not. Okay, so you get a lot of edges, right? I mean, half of all the possible edges are in fact edges. You get a lot of edges. So the complexity is still too high. The number of ones is going to be about n squared. So number of ones in G is like no more than on the order of n squared. If I choose the elements of G to be Bernoulli 1/2, I'm going to get about n squared ones. So my complexity, both encoding and decoding, will be about n squared. That's still too high. Okay, it's better than n cubed. That's still too high. We got to get that down. That's one problem. If I try to do peeling coupled with Bernoulli 1/2 selection of the edges, or equivalently the ones in G. There's another much more serious problem, though. What is it? Bernoulli 1/2 selection of G coupled with peeling.
Yeah, so
Sorry?
yeah, so having just one, or having a row with just a single one.
Very low. Yeah. So when K and N are big, so I mean I need one square with a single one in it, right? So look at it from the vantage point of one particular square. You got K bits. Each one is connected with probability half, right? So your typical square is connected to K over 2 circles. Okay, and of course there's randomness there. Okay, but typical, both the typical and the average square would have like K over 2 edges. Okay, and for peeling to get off the ground, okay, you got to have a square with exactly one edge. Otherwise, peeling won't go past like step 2 or 3 or something. Just say, oh, there's no square with a single edge. Done. Have a nice day. Okay, so that's a problem. It's an even bigger problem, I'd argue, than the complexity issue. So, so peeling terminates at the outset due to no squares with one edge. Okay, so the fix, okay, is just not to do Bernoulli half. Okay, replace that with something else. Okay, so in practice, people still do this randomly. Okay, they just don't use Bernoulli half. Okay, so Bernoulli half would say, for each square, okay, sequence through each circle. So for each transmit bit, cycle through each data bit, and with probability half, connect each pair, and just can do that all the way through. Okay. Okay, so instead what people do is they have a distribution over, they call it a degree distribution, where you pick the degree first of this thing. The degree is how many edges it has. Okay, so if you have k bits, you'd have distribution over 1 to k, like a PMF over 1 to k. You use that PMF to first generate a random number of edges, so maybe it comes out 3. And then you pick a subset of size 3 of the k bits and connect it. And then go to the next one, pick a random degree first, maybe it comes up 1. You pick a random data bit, connect to that one, go to the next one. Okay, this one's 10. Pick a subset of k, subset of size 10 of the k data bits, connect that, and proceed. Okay, so if you do it that way, you can control, how many squares you have with degree 1, i.e. one edge, how many with degree 2, and so on by just tweaking this degree distribution. Okay, and if you choose the degree distribution carefully, you can get the total number of ones in the matrix, i.e. total number of edges way, way down, something on the order of like n log n rather than n squared. Okay. Moreover, okay, you can ensure that you have like the right numbers of squares with the right numbers of edges so that peeling actually succeeds. Okay. This is a very delicate operation, let me tell you. Okay. Just to give you a sense of what can happen. So if you have, for instance, you might say, I think this came up after class last time, you might say, well, let's just designate one square as like our magic square. They'll just have one edge in it. The rest of it, we just do whatever we want. But we'll have like one square to get it started, right? So there's two problems with that. One is the channel might erase this bit. Okay, so you can't put all your eggs in that basket. Moreover, even if it gets through, okay, you've determined one data bit. Okay, you eliminate that from all the other equations. But they had, on average, k over 2 edges before. Now they have k over 2 minus 1. But I need one with one edge, right? Not k over 2 minus 1. I need one with one edge, right? So I need some squares with one edge to get started. When I eliminate the variable from that square that has one edge, okay, I'm going to take some of the variables that had like, degree L, and they're going to have degree L minus 1. So I need some squares to have degree 2, so that when I eliminate a variable, they become a square with degree 1. And then you need some with degree 3 that start out with degree 3, so that when you eliminate twice, okay, you end up with a square with degree 1, and so on. Okay, so in general, when you eliminate a variable, it's like you use up a square with a single degree, and you potentially create a bunch more, like as happened in our example. Okay, so you got to work out all these dynamics so that you're sort of creating and destroying degree 1 squares at the same rate as you go, so that you don't like run out of squares until you've determined all the data bits. Okay, so anyway, so some dynamics there to work out. People have done this. I don't want to get too deeply into it here, but I'll just say so the solution. So replace the Bernoulli 1/2 bit with a more general degree distribution. Okay, and people actually found something called the soliton distribution. In particular, PMF works really well for this. Okay, so that's the distribution they use for generating the degrees. And once you know the degree of a particular node, you just connect to a random set of data nodes with the prescribed degree distribution. Okay, and that brings the complexity of both of these way down, and it makes it so that peeling doesn't terminate prematurely. Okay. Anyways, I just want to do a touch and go on this. This is the analysis and design of these degree distributions is like a very deep topic. It could easily take us the rest of the semester, and if we continue down this path here and start studying degree distributions, we're going to end up with stuff that ideas that don't generalize well. They're very useful for the binary erasure channel, like not necessarily that useful for the channels we care about. So at this point, we're going to put the binary erasure channel aside. I think it's served its purpose. Main messages to take from it. One, you got to mix the bits, but in a particular way. The mixing needs to be kind of long range. Okay, you don't just mix bits that are kind of close to each other in the string. The mixing needs to be done over a very long range. Right, like my G matrix, mixes bits across the whole string, or any one transmit bit here has edges that kind of span, the whole row, the whole string. Right, you don't just have this just kind of does its neighbors, this does its neighbors. So the dependency needs to be long range and erratic, almost random. I would take those two lessons from it. I would take the lesson that decoding is generally more difficult than encoding. Okay. And those are all lessons that are kind of true in general, but particularly easy to see in the binary erasure channel. OK, any questions about BEC or peeling, Gaussian elimination? No? OK, so let's start talking about how to extend this to other channels. So there are a few ways of extending these ideas to other channels. I'm going to focus on one that I think is particularly intuitive for electrical engineers because you can kind of apply like filtering theory to understand it, although it's all discrete. So it's like discrete alphabet filters. And it's also what's used in Wi-Fi. So it's well motivated that way. Okay, so it's called convolutional codes. Okay, so the codes we talked about for the BEC, they were linear, okay, in the sense that I had this fixed matrix, and then you give me the bit string that you want to transmit, okay, and we just multiply it by G. Okay, so it's linear in this sense, like a matrix multiplication. Of course, it's linear over the binary field, not over the reals. Okay, so it's all like mod 2, but modulo that modulo, okay, then you can just view it as linear. The coding schemes we're going to talk about here, they're actually not only linear, they're also causal and time invariant. Okay, because they're causal and time invariant, you can actually view them as like multiplying by like a Toeplitz matrix multiplication, or equivalently just implementing a filter. And this way we'll think about them as just a filter. Okay, so let's start with the definition. So actually it's a bank of several filters. So a convolutional code okay, it's a bank of shift registers with what I will call output taps. Okay, so let me draw a picture to explain what I mean by this. Okay, so a shift register for us is just like a sequence of delay elements, each of which stores 1 bit. Okay, and you have a bank of these things. They do not all need to be the same length. Okay, so some could have more delay elements than others. Okay, and so each of these just store a bit like a flip-flop. Okay, it's like it stores a bit for one time unit. I think in DSP notation you write a Z inverse because it's the Z transform of a unit delay. Anyway, if you've taken a bunch of DSP classes, you probably naturally want to write Z inverse here. If you're more of a computer engineer, then there's like flip-flops. Okay, but anyway, it is like store 1 bit for one time instant, and then they pass the bit on to the next element, and then eventually the bit just falls off. Okay, and you feed in, so the bits that you want to transmit, the data bits, you divide them into streams, okay, and then feed them in here. So I'll call this input stream 0. Input stream 1 up to input stream I minus 1. So we have I total input streams. Okay, and you start with a master stream. You start with just one stream and you just subdivide it. Okay, so take every every ith bit, send it here, and then you know what I'm saying, like take one stream, divide it into I substreams, okay, and then feed these bits in. Okay, so the bits, feed into these shift registers and they kind of march on through. And then you have these output taps, which is XOR a bunch of different values throughout this network. Okay, so you might peel off this value here, it's being currently stored in this flip-flop. Okay, you might take that, and I don't know, this one, and that one. Okay, you take a whole bunch of these things, and you call that an output. Let's call that output stream 0. And you have many of these. Okay, so each one connects to, in general, a different set of bits here in this, among these shift registers. Okay, and I'm not going to, I use I for input. I'm not going to use O for output because it looks like 0. We'll use theta instead. So theta minus 1. Okay, so you have theta, different output streams, I, different input streams. Okay, so the way this works is you take your string of bits that you want to send, you divide it into I substreams. Okay, you just queue up these bits here, and then at each time step, you kind of advance the bits one step, and then just peel off all these bits that are stored in the different flip-flops, XOR that whole set. You get one bit here, you get one bit on the next one bit here. Okay, so that gives you a set of O bits to send, and then advance everything one step. So all the bits advance one step. New bits get filtered in. Some bits just fall off the end. Okay, we get another set of outputs. Keep going. Okay, and then ultimately these output streams will be combined into one master output stream, kind of like the way the inputs were separated to begin with. Okay, and in the end, you've got like a bit stream getting mapped to a bit stream. Okay, that's the idea. When we did the code for the binary erasure channel, the block code as we call it, where we multiply by the matrix, the rate we defined to be k divided by n. It's like the number of bits we were sending divided by the time horizon. K data bits get mapped to n output bits. What would I define the rate as here? It's actually the flip. Yeah, it's like k over n, number of inputs divided by the number of output bits that those cause, right? So here, it's like the number of input bits divided by the number of output bits that those input bits give rise to. So it's I divided by theta. Okay, we'll see there are actually edge effects that crop in. So in practice, when you send n bits, you don't get exactly, when you send k bits, you don't get exactly I, k over theta bits out, okay, because of edge effects. You get a little bit more than that. That's fine. In the large k limit, though, it'll be about that. One more bit of terminology, the constraint length. Constraint length. The code is the length. It's like the number of, by length I mean like number of flip-flops, number of delay elements of the longest shift register. And then this is kind of weird, +1, okay? So the reason they do +1, okay, is that the constraint length then tells you like how many time instance a given bit in the input stream can affect the output, okay? Because you could, I didn't draw it here, but you could have, you're allowed to have a tap like that at the input. So like the current input bit sitting here that hasn't get pulled into any of the flip-flops yet, that can affect one of these outputs, okay? So the total number of time steps in which a given input bit can affect, like, n upper bound, a reasonable upper bound on the number of time slots over which a given input bit could affect the output would be the number of flip-flops plus 1, right? That's for any given filter. You take the longest one, and that kind of that caps, how long a given input bit can be affecting the output. Because eventually, I mean, when it's not at the head of the line, that bit can't affect anything. Okay, and then once it hits the end of the line, it can start affecting the output, but eventually it just falls off. Okay, so constraint length tells you how long you have to wait for that to happen. Okay. So encoding of these things is relatively simple. I'll do an example in a moment. Okay, in practice, you just implement the filter. And these are just like XORs and bit, flip-flops and stuff. So this can be done in hardware, very fast, or in software pretty quickly too. Being a linear time invariant system over the binary alphabet, it's possible to generate like an LTI systems theory for this thing. So you can define an impulse response for any one given filter. Okay, you can try to talk about transforms and stuff, and express any input in terms of a convolution, the impulse response and stuff. We're not really going to bother with that here because it's easier to just implement the filter directly. Just implement the filter. There are two caveats, though, so two complications. You got to specify how it's initialized, okay? Because when you start out, you got input bits coming in, and there's nothing in the delays, right? Delays at the beginning. So you start by just assuming they're all zeros. And, okay, another convention, you always pad the tail end of your transmitted bits with enough zeros to bring you back to the all zero state in the flip-flops. Enough zero padding, let's say. To return to this state. So let me do an example. You'll see what I mean about returning to the zero state. That's the edge effect, by the way, that gives rise to the rate. The fact the rate's not exactly I over theta in practice. Okay, so I'm going to do an example where I is 1 and theta is 2. So we only have one filter. And we have two outputs. And I think I had a particular example in mind here. Let's do this. So this bottom one takes the output of the two flip-flops, and the top one takes the current input bit and the output of the second flip-flop. There's output 0, output 1. Okay, so theta is 1, and I is 1. There's just one input bit here, one input stream. Okay, so suppose you want to send that. Okay, so we're just going to implement this filter. So I'll make a little table here. So remaining input bits. Yeah, the state, and then the output generated. Okay, so we initialize to 0, 0. And the remaining inputs when you start is everything. Now, I'm going to think about, you probably had seen this issue come up in your earlier classes. So I'm going to think about the bits kind of marching in here. Okay, but we usually think of the leftmost bit as being the head, the first bit, right? So if I draw it like this, okay, then it looks like 0 is going in first. So if you want to draw like this, you got to flip it. So just take the bit string, flip it, then they march in like that, right? I'm going to draw it with that convention in this table here. OK, so this is where we start. We're in state 0, 0. These are the remaining bits. So I put it in my picture here. You have a 0, you have a 0, and you have a 1 sitting on this line right here, and these are on deck. OK. So the 0th output is the XOR of this and the 1. So that's 1. And then the output 1 is the XOR of the two bits in the flip-flops. That's 0. So you get 0. OK? Yeah? And now just run it. OK, so each time step, this bit in this flip-flop will fall out. This one moves to the right. An input bit moves in. OK, so now I have 0, 0, 1, 0. Right? OK, and output 0 is the XOR of the rightmost state bit and the current input at the head. So that's going to be 0. And this one's the output of the two state bits, so that's going to be 1. OK, XOR of the rightmost state bit and the input is 1. XOR of the two states is 1. Now, once I advance this one in, I have no input bits left. So you'd say this is not really well defined at this point. But OK, I should have done a different example maybe. So the point is you got to feed in as many 0 bits as you add. You sort of append as many 0 bits as you need to ensure that the system ends up in state 0 at the end. And the decoder needs to know how many bits that is. You can't rely on these zeros clearing it out because the decoder doesn't know that these are both zeros. OK, in hindsight, I should have done 0, 0, 1. That would have made a better example. OK, but I did 1, 0, 0. OK, so it's going to take 2 bits, 2 zeros to clear out the state. OK, so we just assume that we have kind of an extra 2 0 bits that are getting sent. OK, so here you get XOR of these two is 0, XOR of these two is 0. And then advance, we have 0 like this. Of course, you get 0, 0, right? And then, OK, at this point, everyone knows the state's going to be 0, 0. So you would have 0, 0 here. You don't really need to send that, though, because the decoder knows what that is. And you cut it off right there. OK, so bottom line. So bottom line, 1, 0, 0 gets mapped to. OK, you have to decide how you want to like raster these. Do you go like this? OK, do you go like this? OK, that's just a convention. You can do it however you want. We'll go raster like that. So 1, 0, 0, 1, 1, 1, 0, 0, 0, 0. OK, so that's the encoding. OK, this code being rate 1/2, it nominally doubles the number of bits, right? Because every time you feed in 1 bit, you get 2 out. OK. In this case, we fed in 3, and we got 10, right? That's only because of these edge effects here. OK, so we have this extra time where we want to force the system into state 0. That's to help the decoder, so it knows when we terminate where the thing ended up. OK, and that requires sending a few extra bits here. All right, that penalty is quite large when you're sending 3 bits. If you send 200,000 bits, then the extra 5 you pick up or whatever, however many it was. 4 or something. I guess it's 4 bits, right? The extra 4 bits doesn't really matter. OK, that's encoding. People with me? OK, as usual, the real work is on the decoding side. Encoding's easy, so let's talk about decoding. OK, so so for this, I guess we need a channel. So let me specify a particular channel to start, just to kind of like make our thinking more concrete, and then we'll study how to generalize it. So for right now, let's suppose we have a binary symmetric channel. Like that. OK, so a channel that flips bits, each with probability epsilon. So this is called the binary symmetric channel, BSC. As opposed to BEC. OK, so you're the decoder. OK, let's suppose these lengths are hard-coded, just like in ComCloud. Okay, so the decoder knows it's going to get 10 bits. It knows that 3 bits, there are 3 data bits. Okay, from its received 10 bits, it's going to try to guess these 3 data bits. Okay, but the trouble here is that this channel will flip some of these bits. Okay, if it didn't flip bits, then it could, in principle, just kind of study, at each step, given the output bits that it's observing, what the input bit must have been in order to give rise to those, and kind of reverse engineer all this. But the trouble is the channel's flipping some of these bits. You can't rely on that, right? Okay. So what can the decoder do? Okay, so to facilitate decoding, it's helpful to create a state transition diagram. Okay, you've probably drawn diagrams similar to what I'm about to draw in other classes, digital logic and whatnot. Markov chains, if you've taken a class in more advanced random processes. So if you look at this, let's do it in the context of this example. Okay, so this is my system. The state consists of 2 bits. Okay, so there are 4 possible states, right? So 0, 0, 1, 1. I'm going to cheat a bit and look at my notes as I do this because it's very easy to get this wrong and it creates all kinds of trouble if you do. So I'm going to put 0, 1 over here, 1, 0 over here. Okay, so there are 4 possible states for that system. If you are in state 0, 0, okay, and you get a 0, like the input is a 0, okay, then you will return to state 0 and you will output 0, 0. Okay, you understand my convention here? Okay, so if you're in this state and the next input is 0, okay, then you will return to this state. You'll rotate out that 0 bit. This input will get fed into that one and replace it, and you'll still be left with 0, 0, and the overall output will be 0, 0. It's like what happened right in here, right? Like this step, that's exactly what's happening there. All right, on the other hand, if you're in this state and the next input is a 1, the next state will be 1, 0, so I'll give you up here, right? And you output, what do you output if you have, if 1 is your input and you're in state 0, 0, that's actually this picture, right? And then the output will be 1, 0, right? Like that. Okay, so if you're in this state and the next input bit is a 1, you will output 1, 0 and go to state 1, 0. Okay, so you can fill this whole thing in. I'll just write down the answer in the interests of less tedium. Okay, so 1, 0, 0, if you're in state 1 and get an input 1, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1. I think that's it. Let me just spot check these. So the second output bit, the right bit of the output bit is always just the XOR of the state, right? So we can double check if that's true here. So the second output bit should be the XOR of the state. So that's true. And then the first output bit is the XOR of the input in the second output bit, right? So yeah, okay. Seems reasonable. Yeah, did I miss it? Something?
I'm not really sure what the naming convention is. Like, you can like the binary number with a big line through it. And then
Yeah, it's like, this is a slash. So I guess the convention is current state, next state, input, output, like that. Okay, so if I'm in state 0, 0, and the next input bit is 1, I'm going to move to state 1, 0, right? Because this 1, I mean, the rightmost bit in the state will fall off. This one will shift to the right, and the input bit will become the new left state bit. And then just looking at the taps in the example, you'll get a 1, 0 in that case. Is that okay? People check this. We have this right. Is this one right here? If we're going to say 1, 1, and we input is 0. So if I can state 1, 1, and I input is 0, I should output 1, 0. Is that what I have? Yeah, okay. All right, I think we're good. Anyway, you get the idea, right? Okay. All right, so the reason for generating this thing is the following. This is all to the end of decoding. Okay, encoding's done. Encoder, you just implement the filter. That's that. Decoder is what's harder. Okay, so if you're the decoder, let's suppose you hard-code the number of bits. Okay, so the decoder knows 3 bits are being sent, 3 data bits, and it's going to get a string of 10 bits, which is the output of the filter with some bits flipped. Okay, you want to figure out what the input to the filter was. All right. The decoder knows that the encoder starts in state 0 and it ends in state 0, right? Because by convention, you always feed in, an extra 2 zeros here. You append 2 zeros to your input string so that you're guaranteed to end in state 0, 0. Okay, so the decoder knows the encoder starts here. It knows that it ends here. It knows how many transitions it's making because it knows the length of the received string. Okay, and it just needs to figure out what path it followed, right? Because the path indicates what the input bit was. So if it knows that the channel went, you can even follow the example there. So in the example there, it went 1, 0. The output strings were 1, 0. That took me here. 0, 1. That took me here. 1, 1. That took me here. 0, 0. 0, 0. Right? Okay, so in this particular case, the trajectory the encoder followed would just go like that, and then stay here a couple times. Okay, that's not the only one though. Okay, it could go up like that, around. Okay, so there are many. Even when you fix the length, there are many possible paths. In fact, there are 8 possible paths. Each one corresponds to a different choice of the data string right here. Right. So if it's all zeros, okay, then the path the encoder follows is boom, 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 boom. I guess there are 5. 5, right? So boom, 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 boom. Okay, that's one path. The path we had there, 1, 0, 0, 0, which is kind of around this bottom loop here. But there are actually 8 possibilities. Okay, the decoder wants to figure out which path is the right one. That's equivalent to figuring out the data string, the U string. It wants to figure out what path the encoder followed through this state transition diagram, and it knows where it started, and it knows where it ended, and it knows how long it was running. Okay, and it has information about, noisy information about which path it followed because it has a look at these bits with some flips in there. Okay, and the question is, how do we resolve the flips? Okay, if there were no flips, there'd be no problem, right? You could just read out from the output bits, and you can tell exactly what trajectory it followed, and from that you can then pick off the input bits and you're done. Okay, but the flips cause problems naturally. Okay, to resolve the flips, it's actually a kind of involved procedure, but it's sort of cool. So to resolve the flips, we actually expand this thing over time to create what they call the trellis. So where's I have a trellis? No. Okay, missing the trellis picture. We can just generate it from scratch. I guess. Maybe this will help. Okay, so the trellis is just this thing like expanded over time. So you represent different time steps separately instead of just drawing, you know, all the movements on one figure. Okay, so if you start in state 0, 0. You know that's where you initialize to, right? So now in state 0, 0. Okay, you can be the next input bit can be either a 0 or a 1. If it's 0, you stay in that state. So at the next time step, you're still in state 0, 0, and your output is 0, 0. So I'm going to draw it like this. Okay, so if you're in state 0, 0 at time t equals 0, and your input is 0, you output these two bits, and then you go to this state at time t equals 1. Okay. You can also get a 1. In which case you'll move to state 1, 0, and you'll output a 1, 0. Right? So that's these two branches, this one, the self loop, and this one. Okay, those are represented here. Okay. Now at time 1, you can be in one of two places, right? You can be either here again or here. Okay. If you're in state 0, 0, you have exactly the same two possibilities moving forward. Okay, so this trellis is going to be very repetitive over time. Okay. There are only a few things that can happen. So I have the same picture coming out of state 0, right? So if I'm in this state, you can either get a 0 or a 1, in which case the next state's either double 0 or 1, 0. If I'm in state 1, 0, I can go to two different states, right? If the input is a 0, I'm going to move to state 1, 0. And output is 0, 1. Okay, and this is going to get crowded here. Or if the next input's a 1, I'm going to get a 1, 1, right? And I output a 1, 1 in that case. Okay, so the fan out, you know, the edges coming out of a given node are exactly the same as over here. I'm just expanding this over time. Okay, so now at time 2, okay, you can be, at this point you can be in any 4 states. All right, and so now you just kind of continue this pattern here. Okay, so 0, 0 forever after, it's going to have these same two edges coming out of it with the same two things written next to the edges. Same thing for 1, 0. Like that. Okay, now if you're in state 0, 1, you can go back to state 1, 0 if a 1 is inputted. Or you can go home, right? You can go down to state 0 if a 0 is inputted. And that's a 0, 1, 1. And then if you're in state 1, 1, if you get a 1, you stay put and output a 0, 0. And if you get a 0, you're going to end up in state 0, 1. And output a 1, 0. Like that, right? And this is tedious. Okay, but you know, we have the basic pattern now, so it just repeats. Okay, so you're going to keep doing this, and it requires no new thinking at this point to generate the diagram because you just have the same edges cropping up. So I won't write all the strings. I'll just have draw the edges as they would appear. There should be 2 coming out of each one, right? So there's 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. Yeah, I think that's it. and so on. So we need 1, 2, 3. I think I need one more here to make the point I want to make. So let me just draw one more time step. Like that. Okay, so in our example where we're sending 3 bits, okay, and it takes 2 bits to clear out the state, you effectively have like 5 you're transmitting, so you have 5 transitions that occur. Okay, so I'm going to label all these 3 time 0 through time 5. Okay, so I'm going to make the same point I made over here about the decoder trying to figure out the trajectory of the encoder just here instead. Okay, so the decoder knows that the encoder starts here. So this is like the origin. So we know that. We know the decoder knows the encoder ends here, right? Because by convention, you always feed in 2 0 bits at the end to ensure that you're ending in state 0. So you know the decoder knows the encoder is ending there, all right? What it doesn't know is how it gets from here to there. And there are many paths. In fact, there are 8 paths corresponding to the 8 different strings you can be sending. If you send all zeros, the path is just like that. Okay. If you send 1 0 0, okay, then you get 1 0 0, and then you have the 2 zeros for the padding, right? Okay, so the last 2 bits are the padding. Okay, before that you have 3 bits that can be whatever you want, and so you get like 8 possible paths. I've drawn stuff here that doesn't crop up, but you're not going to end up there, right? You know you're ending here at time 5, so you can kind of delete a bunch of stuff off the right corner here if you want, okay, and just save all the possible paths, and there are 8 of them. Okay, so the decoder needs to figure out which is the right path. Okay, each path corresponds to a particular sequence of transmitted bits, right? Like it could be all zeros as the transmitted bits. Right, you can get 1 0 0 1 1 1 0 0 0 0. Okay, that's an example there. So many different possibilities. It's going to get a noisy look at this. The decoder will get a noisy look at this and wants to figure out what is the right path. All right, so if you want to design an algorithm for this, like do some math, okay, that tells us what is the optimal way of finding the transmitted bits or the data bits U. What would be the way of doing that? What mathematical tools can I use in order to figure out what the transmitted bits were? Is what? No? Sometimes people whisper the answer under their breath. We spent like a good several lectures talking about this. I'm intentionally obscuring it, okay, by drawing it in terms of these trellises and paths and so on. But at the end of the day, okay, I'm designing a decoder. It's observing Y, and it wants to guess U. Sorry? Map. Right? In the end, this is going to come down to a big map problem, right? The set of possibilities are the set of strings that we're sending, equivalently the set of paths through this trellis. Those are the set of possibilities, okay? I'm going to observe a set of 10 bits, which is the transmitted bits with a few of them flipped, okay? And I'm going to figure out what is the most likely path through the trellis given the data I've got. This is just an inference problem, okay? So we'll work through this next time. I can tell you, I'll give you a sneak preview of the answer, okay? Any path through the trellis will give me a string of 10 bits, right? Because I got 5 transitions, each one gives me 2 bits. Each path gives me 10 bits. Those are the transmitted 10 bits, if that was the path the encoder followed. I observe 10 bits at the decoder. Okay, those bits I observe at the decoder will generally not correspond to any single path because there are bit flips, there's noise. Okay, nonetheless, put aside the map detection for a moment. Just think about this intuitively. If you had a simple problem like this with 8 possible paths, you observe 10 bits, which path would you go with? What would be your rule? Answer this for me, then we'll go. Yeah? I want the fewest flips, exactly. Each path will give me a string of 10 bits. I observe 10 bits, find the path that gives me the 10 bits that differs in my observed string in as few many as possible. That assumes that this, okay, one quick caveat. That assumes this epsilon is less than half So the channel tends not to flip bits. That's the intuitive case. If epsilon's bigger than a half, then the channel actually flips more bits than it doesn't. So in that case, you actually want to find the path with the most number of differences from your case. But we'll assume epsilon's less than a half, in which case you want the path through the trellis that differs in the fewest number of bits. Okay, we'll work through that on Thursday. I'll see you then.